This video is not going to take a look at how to solve higher ordered linear equations, which is what this chapter is about. It's more going to look at the theory that lies underneath what we do in order to solve these equations. And then future videos will look at the skills we use to actually solve. So looking mainly at theory, we're looking at the question, how do we solve higher order linear differential equations? To do this, we're first going to take a look at what's called a homogeneous higher ordered differential equation. And I want to notice this is different than when we did homogeneous equations in first ordered differential equations. Different use of the word homogeneous here. A homogeneous higher ordered linear differential equation is one of the form a sub n times the nth derivative of y plus a sub n minus 1 times the n minus 1 derivative of y, and so on and so forth until we get down to a sub 1 times y's first derivative and a sub 0 times just the function y. And to be homogeneous, it must be equal to 0. With this homogeneous higher ordered linear differential equation that has constant coefficients a sub n minus 1, and so on, if it has linearly independent solutions, we'll call them y1, y2, 3, 4, 5, all the way up to yn, one solution for every derivative, then the general solution is given by y sub c, we call that y complement. Y sub c is equal to our first constant times the first solution, plus a second constant times the second solution, and so on and so forth until you get to the nth constant times the nth solution. In other words, it's a linear combination of these linearly independent solutions. So if I have solutions y equals e to the 4x and y equals e to the negative 3x, are solutions to the differential equation y prime prime minus y prime minus 12y equals 0, we're going to find the general solution and prove that general solution is a solution to the differential equation. Well, to do that, we're going to say y complement is going to be equal to our first constant times the first solution, which was e to the 4x, plus a second constant times our second solution, which was e to the negative 3x. This is our complementary solution in general form to the differential equation. To show it's a solution, we're going to calculate the first and second derivative and plug these values in. So y complement's first derivative is going to be 4c1 e to the 4x minus 3c2 e to the negative 3x. And the second derivative of y complement is 16c1 e to the 4x plus 9c2 e to the negative 3x. Now we can plug these values in for y double prime, y prime, and y, and see if it does in fact equal 0. So plugging them in, we've got y double prime, which is 16c1 e to the 4x plus 9c2 e to the negative 3x. And we're going to subtract y prime. Y prime is 4c1 e to the 4x minus 3c2 e to the negative 3x. And then we're going to subtract 12 times y. Well, y was c1 e to the 4x plus c2 e to the negative 3x. Simplifying this by distributing the negative through and the negative 12 through, we get 16c1 e to the 4x plus 9c2 e to the negative 3x minus 4c1 e to the 4x plus 3c2 e to the negative 3x minus 12c1 e to the 4x minus 12c2 e to the negative 3x. And the hope is when we combine all these like terms, it should equal 0. Let's see what we get. On the e to the 4x's, we've got 16c1s minus 4c1s minus 12c1s is 0. On the e to the negative 3x, we've got 9c2 plus 3c2 minus 12c2. Sure enough, it equals 0, and so we know our general solution of y complement is the correct general solution. Now that works out great if it's a homogeneous equation equal to 0, but there's a little bit more to solving if we have what is called a non-homogeneous higher ordered differential equation. So these are going to be of very similar form. We'll have a sub n times the nth derivative of y plus a sub n minus 1 to the n minus 1 derivative of y, and so on, all the way down until we get to a sub 1 times y's first derivative plus a sub 0 times y. If a homogeneous equation is equal to 0, a non-homogeneous equation is going to be equal to some function of x. And if y sub c, y complement, is a solution to the homogeneous equation, in other words, if it was equal to 0, not g of x, y sub c is the solution, like we found in part A. And y sub p is a particular solution to the entire thing with the g of x in there, then the general solution is y is equal to the complementary solution from when it equals 0 plus the particular solution. So let's say, for example, y complement is equal to c1 e to the 4x plus c2 e to the negative 3x is a solution to the homogeneous equation y prime prime minus y prime minus 12y equals 0. That's what we just confirmed up in part A. Also, we're being told that y particular equals negative e to the 2x is a solution to y prime prime minus y prime minus 12y equals 10 e to the 2x. we're going to find the general solution. And show it is a solution. Well, we know that y is equal to y complement, which is c1 e to the 4x, plus c2 e to the negative 3x, plus the particular solution. The particular solution given to us was negative e to the 2x. And so this must be our general solution. And we can show it's a solution in much the same way we showed in part A the homogeneous solution worked. We're going to find y prime, which is 4c1 e to the 4x minus 3c2 e to the negative 3x minus 2 e to the 2x. And the second derivative is 16c1 e to the 4x plus 9c2 e to the negative 3x minus 4 e to the 2x. Then we'll plug it into our second derivative, first derivative, and y. And when we do, hopefully we'll get an answer of 10 e to the 2x. Plugging these all in, we've got y double prime, which is 16c1 e to the 4x plus 9c2 e to the negative 3x minus 4 e to the 2x. And then we're going to subtract y prime. Y prime is 4c1 e to the 4x minus 3c2 e to the negative 3x minus 2 e to the 2x. And then we're going to subtract 12y. And y is c1 e to the 4x plus c2 e to the negative 3x minus e to the 2x. And hopefully this will all simplify to the 10 e to the 2x that we're looking for. Distributing the negative through and the negative 12 through, we end up with 16c1 e to the 4x plus 9c2 e to the negative 3x minus 4 e to the 2x minus 4c1 e to the 4x plus 3c2 e to the negative 3x plus 2 e to the 2x minus 12c1 e to the 4x minus 12c2 e to the negative 3x plus 12 e to the 2x. And very similar to last time, as we combine like terms, the 4x's, e to the 4x's, we've got 16c1 minus 4c1 minus 12c1 is 0. We have 9c2 on the e to the negative 3x. 9 plus 3c2 minus 12c2 is 0, e to the negative 3x. And on the 2x's, we've got negative 4 plus 2 plus 12 is 10 of these e to the 2x's, which checks out just like we wanted. So that's kind of the theory behind how we solve these higher ordered differential equations that are linear with constant coefficients. There is something we kind of waved our hands over, though, when we did this, and I want to go back to it. In part A, when we were looking at homogeneous equations of higher order, I said, if we have linearly independent solutions. Well, what does that mean to be linearly independent? And how do we know those functions actually are linearly independent? If functions are linearly independent, what we're saying is no function can be written as a linear combination of other functions. In other words, if I was looking at the functions x squared, x, and 5x minus 2x squared, those three functions are not linearly independent. We actually can say they are dependent, because I could take that first equation, x squared, and multiply it by -2, and the second equation of x and multiply it by 5, and that would equal the third equation of 5x minus 2x squared. I can build the third equation with a linear combination of the other two. So how do we verify that functions are actually linearly independent? Well, to do that, we're going to calculate what's called the Wronskian. And the Wronskian is a determinant. And if you remember determinants from linear algebra, we're going to use that concept here. If you don't remember determinants or haven't taken linear algebra, there's a supplemental video on how to calculate basic determinants I'd encourage you to watch. But the idea of the Wronskian is it's the determinant of the functions f1, f2, all the way down to however many functions we have. We'll say fn. That's the first row. The second row is the first derivative of each of those functions. And then the next row would be the second derivative of each of those functions. And then each row, we're going to continue taking determinants going down until you get to finally a determinant of n minus 1 on each function. Basically, we need to make it a square. And if you calculate that determinant will equal 0 if and only if the functions f1, f2, and so on to fn are independent. Specifically, linearly independent. If it equals 0, we would say the functions are dependent. So let's take a look at an example. Let's take a look at the functions e to the 4x and e to the -3x. We want to know, are these dependent or independent functions? Well, to do that, we'll calculate our Wronskian, which is the determinant of the two functions, e to the 4x and e to the -3x. Because there's two functions, we need two rows, so we'll only do the first derivative, which is 4e to the 4x and -3e to the -3x. Calculating that determinant, we multiply the downhill diagonal to get -3e to the x, adding the exponents, and then subtracting the uphill diagonal, we get 4e to the x, again adding the exponents. And then when we combine like terms, we get -7e to the x, which is not equal to 0. Because this Wronskian is not equal to 0, we can say the two functions are independent. Let's take a look at those three functions we began our discussion on independence with. We talked about the functions x squared, x, and 5x minus 2x squared. If we were to calculate the Wronskian for these, we have the functions x squared, x, and 5x minus 2x squared. Three functions, we're going to need three rows. So the second row is the first derivatives, 2x, 1, and 5 minus 4x. Second derivative would be 2, 0, and -4. And then we want to calculate this 3 by 3 determinant. If it's 0, they're dependent. Not 0, They're independent. Well, the trick with 3 by 3 matrices is I can repeat the first and second row to get x squared and x, 2x and 1, 2 and 0. And the downhill diagonals I'm going to make positive. The uphill diagonals I'll make negative. So we first have negative 4x squared plus, multiplying the other diagonal, is going to be 2x times 5 minus 4x. And the last diagonal, because we're multiplying by 0, is 0. Subtracting, going the other way, we're going to have subtracting 2 times the 5x minus 2x squared. The next diagonal is 0, because we're multiplying by a 0. And the last diagonal, we're going to subtract negative 8. Subtracting a negative makes it positive 8x squared. Let's simplify this expression and see what we have. Distributing through the parentheses, we get negative 4x squared plus 10x minus 8x squared minus 10x plus 4x squared plus 8x squared. Combining like terms, negative 4x squared plus 4x squared is 0. Negative 8x squared plus 8x squared is 0. 10x minus 10x is 0. Because the Wronskian is 0, we can then conclude that these functions are dependent. But we already knew that because we found earlier a linear combination of those functions. All right, so this video took an introductory look at the theory behind solving these linear equations of higher ordered. We looked at what it means to be independent or dependent using the Wronskian. We also looked at finding a complementary solution to the homogeneous case and a general solution, which is equal to the complementary solution plus the particular solution. Take a look at the homework to practice these, and in our next video, we'll actually start solving these equations.